We're surrounded by all these manufactured objects, right? Our phones, the cars we drive, even the planes flying way overhead. And they all look, well, perfect, solid, reliable. But what if I told you that just beneath that shiny, polished exterior, there's this hidden world of stress and strain? A secret life that decides whether that object is going to perform like a champ or fail catastrophically. Today, we're going to peel back that outer layer and explore the secret life of surfaces. It's a question that's driven engineers crazy for decades. You've got this component. It's been machined to perfection. It looks absolutely flawless. But then you put it to work and it cracks. It wears out. It just fails way sooner than it's supposed to. So what's the deal? Well, the answer isn't about what you can see. It's all about what you can't. And this is the key to the whole puzzle: surface integrity. And look, it's not just about how smooth a part feels to the touch. It's the complete story of the surface and that critical layer right underneath it. Its microstructure, how hard it is, and most importantly, the invisible stresses that are locked deep inside. This is probably the single most important factor that determines how a component is going to perform out in the real world. So why are we so obsessed with the surface? It's because that tiny, thin outer layer, that's where all the action happens. Think of it as the component's first line of defense against pretty much everything, and its condition dictates, well, everything. A surface with good integrity can massively extend a part's fatigue life. That's how many cycles of stress it can take before it gives up. It also controls how well it resists just plain old wear and tear, and even how it holds up against corrosion. Bottom line, the entire durability of a part really hinges on the quality of this one microscopic layer. All right, let's get into the science here. The most critical and honestly the most fascinating part of surface integrity is this thing called residual stress. These are forces that get locked into the material during the manufacturing process. It's like a coiled spring of energy just hiding inside, waiting. And depending on what kind it is, it can be your absolute best friend or your worst enemy. And what's great is how simple this concept really is. Think of compressive stress as the hero of our story. It's literally squeezing the material's atoms together, holding any potential cracks shut before they can even start. It makes the part incredibly tough. This is the good guy. But on the flip side, you've got tensile stress. This is the villain. It's actively pulling the atoms apart, creating these tiny microscopic weak spots. It's basically rolling out the red carpet for a crack to form and spread. So the big question is, where do these stresses even come from? Well, they're a direct result of how a part is made. A 2023 study by Holmberg and his team found that the specific manufacturing process you choose, like how a part is 3D printed, can load it up with either that heroic compressive stress or that villainous tensile stress right from the get-go. And this illustrates the point perfectly. They looked at two different methods. When they machined parts made with the PBF-LB process, that's powder bed fusion with a laser beam, they ended up with high tensile stress on the surface. That's a huge red flag for fatigue life. But parts made with the other method, PBEB, which uses an electron beam, had those beneficial compressive stresses just below the surface. Same material, different process, totally different destiny for the part. Okay, now that we get what residual stress is, let's look at the machining process itself, because this is where the magic, or, the damage, really happens. Every single time a cutting tool slices into a workpiece, it's a tiny, violent battle of intense heat and force, and the outcome of that battle gets etched forever into the surface integrity of that part. And research from Hamel and Abid shows just how much control we really have over this. Look at this. If you machine dry with no lubricant, the cutting tool wears out fast. But when you add a smart lubricant like MQL, that's minimum quantity lubrication, and especially when you combine it with cryogenic CO2 cooling, the tool wear just plummets. A happier tool means a much better cutting process. And here's the payoff. The exact same advanced cooling that saved the tool, it also creates a dramatically smoother, higher quality surface on the final part. Less heat and less friction during that battle means less damage, a better finish, and at the end of the day, much better surface integrity. It is a perfect win-win. So, knowing all this, how do engineers actually take control of these invisible forces to create those perfect surfaces? Well, it turns out they have an entire toolbox of advanced techniques designed to do exactly that. It really boils down to three main strategies: using cutting-edge coatings on the tools, bringing in smart lubrication and cooling methods, and of course, fine-tuning every little parameter of the machining process itself. Let's take a quick look at the first two. First up, coatings. I want you to think of these like microscopic armor for the cutting tool. They're these super hard materials like titanium, boron, tungsten, applied in incredibly thin layers. This creates this slick, super durable barrier between the tool and the part. It lets the tool slice material away cleanly with a lot less force, which means way less friction and heat, and that protects the brand new surface from getting damaged.
Next in the toolbox is smart lubrication, and we are way beyond just squirting some oil on there. We're talking about things like MQL, which delivers this precise aerosol of oil right where it's needed. Some other methods even mix nanoparticles into the fluid to cut down friction even more, or they use blasts of super cold CO2. All of these techniques are about surgically removing heat right at the cutting edge, which prevents thermal damage and leaves you with a pristine surface.
Okay, so this all sounds amazing in a lab, but where does it actually matter? The answer is everywhere that failure is simply not an option. Let's look at two completely different worlds where surface integrity is absolutely critical. First up, aerospace. When you're dealing with jet engine components or critical parts of a plane's structure, fatigue life isn't just a nice-to-have, it is a life-or-death requirement. Take the titanium alloys they use in turbine blades. They're incredibly strong, but they are notoriously difficult to machine. The whole goal here is to use those toolbox techniques we talked about, like nanoparticle MQL and those special coatings, to intentionally create high levels of that heroic compressive stress. This acts like a built-in defense shield, actively fighting against fatigue cracks for the entire life of the component. Now, let's do a complete 180 and jump to a totally different field, the super high-precision world of optical manufacturing. In this world, they're machining things like KDP crystals, which are used in really advanced laser systems. These materials are unbelievably brittle. I mean, the slightest imperfection, even a microscopic crack just under the surface, can completely ruin the crystal. So the goal here isn't just strength, it is absolute flawless perfection. Researchers are even using special bio-based lubricants just to create this super stable film that minimizes friction and thermal shock, ensuring a perfect surface with zero hidden damage. So at the end of the day, what all this research really tells us is that the stuff we can actually see, the polish, the shine, that's just a tiny piece of the puzzle. The true measure of quality, of durability, of reliability, it all lies in that invisible world just beneath the surface. And that kind of leaves us with one final thought. As we keep engineering things that are smaller, faster, and more powerful, everything from microchips to medical implants, the importance of that surface just gets bigger and bigger. So is it possible that the next great leap in engineering won't be about discovering some brand new material, but about finally mastering this invisible, microscopic world on the surfaces of the materials we already have?